Welcome to our video on Stokes' theorem, one of the most elegant and powerful theorems in vector calculus. Stokes' theorem connects a surface integral of the curl of a vector field over a surface to the line integral of the vector field around the boundary curve of the surface. Intuitively, it relates the microscopic circulation or curl of a vector field on a surface to the macroscopic circulation along the boundary of that surface. You can think of it as a generalization of Green's theorem to 3 dimensions. Let's begin with the formal statement of Stokes' theorem. Let S be an oriented smooth surface that is bounded by a positively oriented, piecewise smooth, simple closed curve C. Let F be a vector field whose components have continuous partial derivatives on an open region in 3-dimensional space containing S. Then the line integral of F around curve C equals the surface integral of the curl of F over the surface S. In mathematical notation, we write this as the closed loop integral around C of f dot d r equals the double integral over S of the curl of f dot ds. To visualize Stokes' theorem, let's consider a simple example with a circular surface. Here we have a flat circular surface S in 3-dimensional space. The boundary of this surface is the circle C. Now imagine a vector field F flowing across this surface. The vectors might have different magnitudes and directions at different points. The curl of this vector field, represented by nabla cross F, measures the rotational tendency of the field at each point. If we imagine placing tiny paddle wheels on the surface, the curl determines how fast and in which direction these wheels would rotate. Stokes' theorem tells us that the total circulation of the vector field around the boundary curve C is exactly equal to the total curl integrated over the entire surface S. Let's explore some key concepts essential to understanding Stokes' theorem. First, we need an oriented surface. This means we choose a specific side, or normal direction for the surface. This normal direction is represented by a unit normal vector n perpendicular to the surface at each point. Next, we need a positively oriented boundary curve. The positive orientation of curve C is determined by the right-hand rule. If you curl the fingers of your right hand in the direction of the orientation of C, your thumb points in the direction of the normal vector n. Finally, the curl of a vector field, nabla cross F, measures the rotation or circulation density of the vector field at a point. For a vector field F with components P, Q, and R, the curl is given by this formula, involving the partial derivatives of the components. Stokes' theorem has several important applications and benefits. One major application is evaluating difficult line integrals. If a line integral around curve C is hard to compute directly, Stokes' theorem lets you convert it into a surface integral, which might be easier. Conversely, if a surface integral is challenging, you can convert it to a line integral instead. An important advantage is that you can choose any surface S that has the same boundary curve C. This flexibility allows you to select the surface that makes your calculations easiest. In physics, Stokes' theorem is fundamental to understanding electromagnetic fields, fluid dynamics, and many other phenomena where we need to relate circulations to curls. Let's solve a specific example using Stokes' theorem. Let's say we have a vector field F equals the vector negative y squared x z squared, and let C be the curve of intersection of the plane y plus z equals 2 and the cylinder x squared plus y squared equals 1, oriented counterclockwise as viewed from above. We want to find the line integral of F around curve C. Step 1, we compute the curl of F. The curl of F equals the vector 0, 0, 1 plus 2y. Step 2, we choose a surface bounded by C. The natural choice is the part of the plane y plus z equals 2 inside the cylinder x squared plus y squared equals 1. Step 3, we need to find the normal vector to the surface. By taking the cross product of the tangent vectors, we get the normal vector 0, 1, 1. Step 4, we set up the surface integral. The surface integral becomes the double integral of the dot product of the curl 0, 0, 1 plus 2y, and the normal vector 0, 1, 1 over the domain D. This simplifies to the double integral of 1 plus 2y over the disk x squared plus y squared less than or equal to 1. Step 5, we evaluate this integral using polar coordinates. After substituting our sine theta for y and integrating, we get pi. Therefore, the line integral of F around curve C equals pi. In conclusion, Stokes' theorem is a powerful mathematical tool that connects surface integrals of curl to line integrals around the boundary. It generalizes Green's theorem to 3 dimensions and provides a way to translate between microscopic and macroscopic circulation. The flexibility to choose different surfaces with the same boundary makes it a versatile tool for solving complex problems in mathematics and physics. By understanding Stokes' theorem, you gain insight into the fundamental relationships between vector fields, surfaces, and curves in 3-dimensional space. Thank you for watching. If you found this helpful, please like and subscribe for more math videos.